hello, chemistry students. Today we're going to take a look at limiting and excess reagents. These are a really key concept to solving harder problems based around the mole ratio, which are quite common in chemistry, both in Year 11 and in Year 12. We are currently exploring the first two inquiry questions. So this is continuing on with the work we have been doing in class on chemical reactions, stoichiometry, and the mole concept. All right, so it's very normal to get a pretty simple mole ratio problem based around this sort of question here. So if we take a look at this, from the following unbalanced reaction, how many grams of sodium hydroxide, NaOH, will be required to fully react with 3.10 grams of sulfuric acid, that's H2SO4. And we have an equation that's been given to us. Now, I'd like to remind you that once we have a balanced equation, the ratio of moles is just like a cookie recipe, okay? And we can use that to help us work out the quantities of other reactants and products across the reaction. So, how would you go about solving this sort of problem? Pretty straightforward. All right, there's 4 steps to it. You need to balance the reaction, convert the known amount of reactant to moles, use the mole ratio to find the moles of the other reactant, which we don't know the amount of, and convert the moles of that reactant to the mass of sodium hydroxide that we will need to react with our 3.10 grams of sulfuric acid. All right, so this is one of those questions where I'm going to say, if you are feeling brave, and you should be, hit pause, give it a go. All right, I'll wait, don't worry. All right, so 1, 2, 3, hit pause. All righty, I'm assuming you've given it a go and now you're coming back to it. Let's break it down in terms of how we would go about solving this. The first step, we need to balance the reaction. So we take a look at this. All right, on the reactant side, we have 1 sodium atom. On the product side, we have 2 sodium atoms. So yeah, the reaction's not balanced. Turns out that we'll have 2 moles of sodium hydroxide reacting with 1 mole of sulfuric acid to form 2 moles of water and 1 mole of sodium sulfate. Step 2, convert the known reactant amount to moles. Or again, all we're doing here is we are taking what we know. We know we have 3.10 grams of sulfuric acid. We're going to take our mass of 1 mole of that, all right, which is 98.9 grams, and we're going to divide our mass by that to work out the moles of sulfuric acid. Now, I've got it there in scientific notation, all right? On your calculator, it's probably going to look a little bit different. Now, our next step after this is to take the known moles and use the mole ratio to find the moles of the reactant. And we took at the mole ratio of sodium and sulfuric acid. We can see that it is a 2-to-1 molar ratio, respectively. All right. So if we have 3.16 times 10 to the minus 2 moles of sulfuric acid, we know, because it's a 2-to-1 ratio, that we have to have twice that quantity of moles of sodium hydroxide, which comes out to 6.32 times 10 to the minus 2 moles of sodium hydroxide. Okay, now, final step, we just need to convert our now known quantity of moles for our sodium hydroxide to a mass. And we do that by timesing it by the molar mass, which for sodium hydroxide happens to be 40 grams per mole. All right, pretty straightforward, comes out at 2.53 grams of sodium hydroxide. And I like to cap off all of my answers to problems of this nature with a little therefore statement, just like a mathematical proof. Therefore, we need 2.53 grams of sodium hydroxide to fully react with 3.1 grams of sulfuric acid. Solving this sort of simple mole ratio problem, they always follow the same step, okay? And that means that there is always going to be a similar set of steps where you're going to need to balance the reaction, convert the amount of known reactant, 2 moles, use the mole ratio to work out the moles of your other reactants or products, and then convert the mass of that moles that you've worked out to the mass of the respective reactant or product. The steps are always going to be a variation of these 4 steps. All right, so while it may seem hard, understand that once you've mastered these 4 steps, you can solve any of these problems, because they are, all of them tend to be very, very, very similar. All right, that brings us to the next curveball that chemistry teachers love to throw at their students, and that is limiting and excess reagents. And what we will look at this is, food's actually a really good analogy. So if we take a look at the scenario where we have 5 hot dogs and 4 buns, all right, how many complete hot dogs can we make? It's pretty straightforward. Our brain just tells us immediately we can make 4 hot dogs in a bun, and we have 1 extra hot dog left over. If we apply this to a chemical reaction, and we can do this because we are keeping track of the number of particles that are in ratio across that reaction. In this case, the buns is what is limiting us to produce complete hot dogs. We can, in theory, produce 4 complete hot dogs. And so we introduce some new terminology to our understanding of chemical reactions, and that is the smallest molar quantity that we have is our limiting reagent. Now that we need to obviously be mindful of the ratio of moles, okay? The amount of product that we can form if all of the reactants react is the theoretical yield. That won't always happen. Sometimes we end up with a mixture of products and reactants after our reaction takes place. All right, and any leftover starting materials is excess reagent. All right, so if we were to take a look at this, just using another example with food, how many burgers can we make with what we have in front of us? So 1 hamburger is made from a bun, a single slice of cheese, a couple of pieces of lettuce from the bundle of lettuce we have there, and a meat patty. How many can we make? If we have a look at this, the answer is 3. Okay, and that is because we are limited by the smallest amount of material we have, which happens to be our bundles of lettuce. So we can make 3 complete burgers. All right, so applying this to a mole problem does make it a little bit more complex problem. What we need to do is we need to find the limiting reagent as part of the steps we go about to solving the reaction. So if we take a look at the following example just here, what is the limiting reagent if we start with 2.8 grams of aluminium and 4.25 grams of chlorine? The way you differentiate this sort of problem from the prior mole ratio problem is you are given 2 masses. If you are given 2 masses, that is a hint that there is going to be a limiting and excess reagent. All right, they've given us an equation just here. And so to solve this problem, the steps we should take: check that the reaction is balanced. That's first step, any type of chemistry problem. Check for a balanced reaction. Step 2, convert both amounts to moles. And step 3, using the mole ratio, work out which of those 2 quantities of moles is the limiting reagent. All right, so at this stage here, we have how we need to solve this. Give it a go yourself. Hit pause. All right, 1, 2, 3, pause. I'll wait, and then I'll go through it. All righty. So step 1, we need to check if this reaction is balanced. So let's take a look. We have 2 moles of aluminium on the reactant side and 2 moles on the product side. We have 3 moles of Cl2, so 3 moles of chlorine on the product side, and we have 2 times 3 chlorine, so 6 So we have the same amount of chlorine. We have a balanced equation. That's convenient. All right. Step 2, we need to convert our masses of aluminium and chlorine to moles. And we do that by dividing the mass of each by the atomic mass of each element, which we can get from the periodic table. That comes out at 1.04 times 10 to the minus 1 moles for aluminium and 5.99 times 10 to the minus 2 moles for chlorine. Step 3. Now what we have to do is we need to find the limiting reagent using the stoichiometric ratio. So if we take a look at our reaction, we can see that we need 2 moles of aluminium to react with 3 moles of chlorine. So that means for every 0.67 moles of aluminium, we have 1 mole of chlorine. Now, if we take a look at our actual ratio of moles, by putting our moles of aluminium above our moles of chlorine, we can see that we have 1.74 moles of aluminium on top of 1 mole of chlorine. Now, this tells us that we have much more aluminium present than we have chlorine, which, because that is greater than our stoichiometric ratio, that means we have more than enough aluminium to react with each mole of chlorine that is present. Therefore, chlorine is our limiting reagent. Okay, so thinking about how we solve our more complex mole ratio problems, again, there is a common theme to this sort of problem. One, we need to balance. So one, we need to balance the reaction. 2, work out the moles of each reactant. All right. 3, using the mole ratio, work out which of those reactants is the limiting reactant. 4, using the moles of the now identified limiting reagent and the mole ratio, work out how much of the other material will actually be consumed in the reactant. 5, convert the moles to mass to show how much product forms in the reaction. Now, again, really want to just highlight, these might not seem like easy problems when you're first starting out, but once you get what's going on, it is always a variation of these steps. Thank you for watching the video. Hopefully this has helped you get your head around mole ratio problems. Let's get on with the lesson, people. Bye-bye.